check this out. Isn't it cool? I came across it while browsing for inspiration and it instantly caught my attention. I've been wanting to dive into shader development and these visuals really inspired me to try and bring the look into a game. The style is called Vaporwave. It's all about neon colors, glitchy effects and retro futuristic vibes. Bold pinks, purples and blues combined with dreamy surreal landscapes. This particular image really stood out to me, so I'm using it as a base for the project. I won't be recreating it exactly, but I will aim to capture its essence. I'll walk you through each step and share what I've learned along the way. The basic elements are already set up in Unity, so let's bring this into life. Let's get started. If you're new to shaders, like I was at this point, here's a quick and honestly unfair summary. Essentially, shaders are small programs that run on your GPU, controlling how things are drawn on the screen. We'll be working with fragment shaders, and their job is to decide the color of each pixel based on data like its position and the object it belongs to. So we need to figure out how to describe the look of this sun in terms of individual pixels. Looking at the reference image, the sun has two main features. It's got this smooth gradient that transitions from a saturated pink to a bright orange, and then there's the pattern of horizontal lines that cut across it. There's also a bit of glow around it, but overall the design is very flat and minimalistic. Let's tackle the gradient first. We want to transition from pink at the top to orange at the bottom. In shaders, colors are represented by numerical values for the red, green, and blue components. Pink and orange are just combinations of these values, and we can find the colors to blend between them by linearly interpolating each component. Since shaders work at the pixel level, we need to determine, for each pixel, how far along this interpolation it is. For a vertical gradient, we can use the pixel's y-coordinate to decide the position in the transition. Essentially, this y-coordinate tells us how much of the pink or orange color should be mixed at each pixel. By the way, I'm using Unity's Shader Graph, a visual tool that lets you build shaders without writing any code. For this, there's a handy gradient node that makes things quite straightforward. However, it's still important to grasp the underlying theory, as things can get more complex. Let's dive into another sort of detailed example, and then we'll pick up the pace. The lines. To create a pattern of alternating, let's say, black and white lines, we can draw on a concept similar to the gradient. We want once again to use the vertical position to decide on a pixel's color. The main difference is that this time we want to create a repeating pattern. One effective way to achieve regular repetition in mathematics is by using oscillatory functions, such as the sine function. The sine function naturally oscillates between two values. We'll use it applied to the vertical axis to create a wave-like pattern. The value of the sine function will vary between -1 and 1, and we can interpret these values to represent the intensity of color or, again, as the controller for a linear interpolation between black and white. For simplicity, we scale the sine function output to range from 0 to 1, where 0 is black and 1 is white. To make the lines more distinct and less smooth, we adjust the sine function to create more abrupt color transitions. By introducing a threshold and mapping ranges of values to specific colors, like mapping values between 0 and 0.5 to black and values between 0.5 and 1 to white, we flatten the curve of the sine wave. This results in squared-off lines rather than soft transitions. Now that we've created both the gradient and the line pattern, we can combine them for the final effect. The key idea here is that multiplying a color by a value between 0 and 1 controls its brightness. 1 leaves it unchanged, while values closer to 0 darken it. In this case, we multiply the gradient color by the value from the line pattern for each pixel. The gradient sets the base color, and the pattern determines how much of it gets darkened. By doing this, we essentially layer the two effects. To keep things flexible, I made the shader parameters adjustable, allowing for tweaks to the gradient colors, line frequency, thickness, and other properties to experiment with different styles. Looks good, right? Let's move on to a more interesting challenge. Let's revisit the reference image, now focusing on the terrain. The key features include lines, again, that trace the mountain ridges. These lines seem to react to lighting in a way that makes the terrain appear more dynamic. The brighter areas are also highlighted with a different color, adding depth to the scene, and the colors are minimal. Blue for the lines, pink for the illuminated areas, and the dark, almost black background. These are also highly saturated, vaporwave style. Let's break it down again. Lines first. We follow the same pattern technique we developed for the first shader, this time with a flat, dark color for the background. For the lines, we use a vibrant blue, setting it also as an emissive output, so they'll shine even in dark areas. However, this time I want to add a few enhancements to refine the shader. First, let's control the orientation. I want the lines to follow the mountain shapes and to be able to adjust their direction. The direction of the pattern is determined by the input to the sine function. So far we've used the vertical axis, but now we need it to align with the xz plane of the terrain. Think of it as if projecting the lines from above. To add flexibility, we can also rotate this projection. The math looks like this. It's only adjusting the x and z components with theta, a value to control the angle of the lines. It may seem intimidating, but once you get the concept, there are plenty of online resources to guide you through it. The idea is simply to create a sine wave pattern across the xz plane with an adjustable angle. Next up is improving how we control line density. So far I've been adjusting the frequency of the sine wave by multiplying the input by a numeric parameter. This works, but we can make it more sophisticated by adjusting the density based on the height values of the terrain, or more specifically, the steepness or rate of change in the surface. Simply put, I want fewer lines in areas with rapid elevation changes, like steep cliffs, to reduce noise and make the visuals cleaner. We can enhance this by building on the previous math, adding another layer to make the oscillatory function even more customizable. It does feel like a bit much for this video, but I wanted to show it as an example of how you can keep refining the effect by stacking simple mathematical steps. Now, I'll flash the new formula on the screen. Hopefully that didn't feel like a jump scare, but don't worry, there's no need to dive into the details. Honestly, I don't think I could explain it fully anyway. The important takeaway is that this formula adjusts the density of the lines based on the slope of the terrain. Nice, one more enhancement. Let's talk about light and its influence on the terrain. If we look closely at the reference image, it seems like the line density changes based on how bright the surface is. More lit areas appear to have more clustered lines. I want our implementation to respond to lighting too, but I'll take a slightly different approach, mainly because I don't want to overcomplicate the shader. Instead of adjusting the line density, I'm going to tweak the line brightness, based on how much light hits the surface. This will still give us the effect where dimly lit areas have fainter lines, adding contrast and depth. So, how do we figure out light levels for each part of the surface? We can break down how light behaves and figure it out using some simple logic. We'll need two key pieces of information: the direction of the main light source, which is data we have available, and the normal vectors of the terrain. By the way, these normals are basically vectors pointing directly out from a surface, perpendicular to it, showing which way it faces. Now, if the direction of the light is opposite to the surface's normal, that spot is probably well lit. On the other hand, when the light and the normal are pointing in the same direction, it's more likely to be in shadow. Of course, this is a simplified version, but Unity is already handling most of the heavy lifting when it comes to lighting. This is just to add our own tweaks to the material. To make this calculation, we can use a nice little tool you might remember from algebra called the dot product. The dot product helps us see if two vectors point in the same direction. If the result is 1, they are aligned, if it's 0, they are perpendicular, and if it's -1, they are opposite. That's exactly what we need, though I've inverted one of the vectors to make it more intuitive, so that higher numbers correspond to more light hitting the surface. Now, this number directly influences the brightness of the lines, meaning more lit areas will have brighter lines, while darker areas will have dimmer ones. To finish up the terrain, we need to tackle those pink highlights we saw in the reference image. Since they appear in the brighter areas, we can recreate them using a similar technique as with the line brightness. We'll compare the light direction and the surface normals again, but this time we'll use a threshold to split the surface into two groups, well lit and shadowed. For the well lit areas, I added a pink overlay to make them pop, capturing that distinct highlight effect from the original artwork. Just like with the sun shader, we have plenty of adjustable parameters here: line thickness, highlight color, light influence, and more. I think this looks pretty good. Now let's shift our focus upward and continue expanding our shader toolkit as we work on the skybox and introduce more techniques along the way. Back to our reference, the main features are a horizon gradient and small dots of varying brightness and color for the stars. We already know how to handle gradients, and we want another vertical one here, so that's easy. Let's focus on the stars. To start, I found an image with lots of little dots and set the shader to pick colors for each fragment based on that. When an image is applied to a 3D surface to add detail, it's called a texture. The texture doesn't have to be a perfect night sky. We'll customize it soon. The interesting challenge here is mapping a flat 2D image onto the spherical shape that represents the sky in our game. You can see the challenge, right? Mapping flat 2D images onto 3D is tricky, or the other way around even, like creating accurate maps of Earth. While there are several ways to wrap a texture around the sphere, most aren't as simple as they might seem. However, for our use case, we can use a more straightforward approach. Take the X and Z positions in the world and divide them by the Y position. This projects the texture along the XZ plane and wraps it vertically, effectively dividing the sphere into northern and southern hemispheres. The method accounts for the vertical component to try and wrap the texture as smoothly as possible, but it still creates some distortion near the poles, with stars clustering around the horizon. But for our needs, it works surprisingly well and in my opinion gives a convincing starry sky. This is looking good, but I'd like more control. I don't want the texture alone to dictate the star formations. To add variation, we'll use random values in the form of noise. Think of noise as a grayscale texture where each pixel holds a random value between 0 and 1. How random it looks depends on the noise generation algorithm. How we apply these values is up to us, and I'll combine them with the texture in two ways: to control brightness and to add some color. By multiplying the texture by the noise, we introduce variation in color intensity. Each pixel gets a color based on our texture to sphere mapping, then that color is adjusted using the noise value at the same position. This creates a more natural scattering of stars with random dimming that makes the formations feel less uniform. We'll also use noise to assign random star colors. For example, we can split the noise values into 3 ranges, each corresponding to a different color. I chose white, blue, and pink to match the vaporwave aesthetic. In a way, the noise acts as a color selector for the stars. Pretty neat, right? First we use the noise to control brightness, then leverage it again to introduce color variation. With a few minor tweaks here and there, we now have a beautiful, customizable starry sky inspired by the original artwork. With all the main elements in place, we've recreated the reference image for our vaporwave scene. But I can't cover shaders without including a classic water effect, and this planet is practically begging for a little lake. Let's dive into creating a water material, a common exercise when learning shaders. Since this wasn't part of the reference image, we'll set our own goals. The idea is to create a shader for a simple plane mesh to represent our lake, with a solid base color, subtle wave movements, and light reflections on the surface. First up, let's tackle the movement part. We've been working with fragment shaders so far. Here we want to use something called a vertex shader. As a very unfair summary once again, vertex shaders are responsible for processing each vertex of our mesh, adjusting their positions based on various inputs to create different effects. In our case, we want to create the illusion of moving water. We can once again use noise for this, although this time I will animate it, introducing an offset that changes over time, giving the water a dynamic and realistic flow. Next, we add highlights to simulate the way light reflects off the water. I'm also using noise patterns one last time, now thinking of them as a way to build a normal map. A normal map represents the surface normals at each pixel, which affects how light interacts with the surface, as we've seen before. Again, animating it over time, we make the reflections shimmer and change in a natural way. And here's the result. We can also adjust parameters like the wave speed, the intensity of the reflections, or simply the color to fine-tune the appearance of our lake. Let's take a moment to appreciate the final result. By the way, throughout the video I've been showcasing the scene with post-processing effects applied. To give you a better sense of their impact, let's briefly compare how the scene looks with and without them. For instance, we used bloom to make the lights and colors pop, along with color adjustments to enhance the overall visual appeal. These effects play a significant role in creating a polished final image. Now, there are areas for improvement. We are experiencing some aliasing on the ground, especially in areas farther from the camera. Aliasing occurs when a detailed image is rendered at a resolution too low to accurately capture all the information. The rendering engine must decide which pixels to display, and with sharp patterns, like our lines, it struggles to downscale while preserving the original design, resulting in visual artifacts. This could be addressed by incorporating textures and using techniques like MIP maps or anisotropic filtering. And yes, shader development comes with its fair share of intimidating terminology, but to briefly explain, MIP maps are low-resolution versions of textures that help the renderer select the appropriate detail at different distances, while anisotropic filtering improves texture quality when viewed at steep angles, which is particularly relevant here. We're also seeing some flickering stars near the horizon, likely another aliasing issue, though I'll admit I'm not entirely sure. Lastly, some of the ground lines have sharp angles that could be smoothed out with more refinement. That said, I'm really proud of how this turned out. I think we've captured the dreamy neon vibe of the vaporwave style quite well. It's been exciting to see just how much you can achieve with a basic understanding of shaders. and breaking down a reference image into its main features and building it piece by piece is a strategy that really works. I've learned a lot throughout this process, and I hope you've enjoyed following along. See you next time.